Imagine shining a light on something, and just by watching how that light changes, you can start to see this hidden, intricate bands of atoms. They're
Yeah.
tiny components.
Yeah, it sounds almost deceptively simple, doesn't it? But that very idea, that core concept, is what allowed physicists, these pioneers, to really see the quantum world.
And manipulate it
Yeah,
in ways nobody thought possible before.
exactly. Which is why we're doing this deep dive today. We're looking at Alfred Kastler's work.
Specifically, his 1966 Nobel Lecture, right? Optical methods for studying Hertzian resonances.
That's the one. And it's not just, a dusty old document. It's really a window.
A window into how they used light, cleverly, to just revolutionize quantum mechanics.
So our mission really is to unpack it all. The core ideas, the experiments, some were pretty ingenious, and sometimes surprising discoveries.
How they managed to essentially see inside atoms and control them. And we want to explore what this means for you, the curious learner, how these fundamentals laid the groundwork.
Definitely. Okay, so where do we start? Kastler's beginnings.
Let's do that. He was at the École Normale Supérieure in Paris. And quantum physics, well, it wasn't really taught much in France back then.
Right, so his teacher, Eugene Bloch, introducing him to it was quite significant.
He talked about being in the right place.
Mm.
And he was heavily influenced by some key texts, too.
Oh, absolutely. Sommerfeld's book, Atombo and Spectralinean, Atomic Structure and Spectral Lines,
Fantastic.
and also the work of Wojciech Rubinovich, both really hammered home this central idea.
The conservation of angular momentum. That's the key principle, isn't it?
That's the one. Specifically, how it applies when light electromagnetic radiation interacts with atoms. It just captivated Kastler.
And it wasn't just theoretical fascination. It led directly to interpreting things like selection rules.
Yeah, for the azimuthal quantum number and polarization in the Zeeman effect.
Which, just to remind everyone, is when an atom's energy levels split in a magnetic field. So this principle explained why certain transitions happen and others don't, and why the light has certain polarizations.
Exactly. The thinking was that photons, these light quanta, carry angular momentum, like tiny spinning tops.
So plus h bar for right circular polarization, sigma plus.
Right. And minus h bar for left, sigma minus. Natural light is just a mix, canceling it out overall.
Okay, so we've got this core theoretical idea. How did it connect with what people were actually seeing in labs?
Well, around 1931, there were these pioneering observations by W. Hanlel and R. Baer, independently.
On Raman spectra, right. That's the light scattered off molecules.
Yes. And they found something interesting when they looked at the polarization of this scattered light at right angles to the incoming beam.
They could classify the Raman lines into two types.
Pretty much. Deep polarized lines with this specific factor of 67,
Okay.
and polarized lines which, kept a fair bit of their polarization.
And Platschek's theory connected this to the molecules themselves.
It did. George Platschek linked the depolarized lines to things like molecular rotation, the molecule spinning.
And the polarized ones.
Those were linked to totally symmetric vibrations, where the molecule vibrates but kind of keeps its overall shape symmetrical.
But then Hanel and Burr noticed something else, something crucial.
Right, when they used circularly polarized light to begin with.
What happened to the scattered light?
For those symmetric vibrations, the scattered light kept the same circular polarization.
Okay.
But for the non-symmetric ones, it reversed it.
And Kastler saw this and immediately thought,
Angular momentum. He put out a note in 1931 saying this was a direct consequence of angular momentum conservation in light scattering.
so light wasn't just bouncing off. It was exchanging this fundamental quantum property.
Exactly. It opened up a whole new way to probe what was happening inside.
Now, you mentioned Jean Caban also explained this result.
He did, yeah, using classical ideas about polarizability. But Kastler's insight, recognizing the quantum angular momentum exchange, that was the key step forward, really. And his note actually came out slightly before Caban's work on it.
It shows how quickly he grasped the implications. But, science isn't always smooth sailing. Not every experiment works first time.
Oh, definitely not. Kastler himself had a go in 1931 trying to show a transverse component of angular momentum in photons.
Using linearly polarized light.
Yeah, from a rotating atomic oscillator. It didn't work.
A failed experiment. Robert Frisch apparently found similar results. Must have been frustrating.
You'd think so, but sometimes those failures push you in new directions.
So instead of giving up, he doubled down on the fundamentals.
Pretty much. It led him to systematically look at all the consequences of angular momentum conservation, in scattering, in fluorescence.
And that led to this idea of exciting atoms in steps.
Exactly. Nudging them up the energy ladder one level at a time using carefully chosen light.
And you could control this with polarized light.
Yes, polarizing different monochromatic beams let you guide the atoms up these energy steps.
He tested this on mercury atoms.
He did. And the fluorescence they observed showed that, yeah, you could actually get a decent number of atoms into these higher excited states this way.
So proving you could use light, not just to observe, but to actively manipulate atomic states.
Precisely. And this work on Hertzian resonance, using radio frequencies, it didn't come out of nowhere. It built on earlier stuff.
Like Robbie's work, and Lamb and Rutherford.
Absolutely. Robbie and his students, and then Lamb and Rutherford's famous work on hydrogen, which was huge for quantum electrodynamics. Kastler was standing on the shoulders of giants, so to speak.
But not every idea panned out immediately. You mentioned Francis Bitter.
Right, an American physicist. He proposed extending radio frequency spectroscopy to excited states. But his specific approach turned out to be, well, inexact. It shows the process, the trial and error.
Science in action. And this led to him reconnecting with Jean Brossel.
Yes, his former student, who was over at MIT, they corresponded, discussed the problems.
And decided they needed something simpler.
Exactly, a very simple technique, as they put it, more direct.
And that technique was the double resonance method. Sounds complex.
Well, the name might, but the idea was elegant. It combined magnetic resonance using radio waves to flick spins in a magnetic field.
Like in MRI.
Kind of, yeah. Combine that with optical resonance using light to excite the atoms in the first place.
A two-pronged attack.
Precisely. And it gave them this powerful new way to study atoms. Very precise, very efficient.
And the core of this was optical pumping. Can you break that down?
Sure. The idea is you use that circularly polarized light again, sigma plus or sigma minus,
Okay.
and you literally transfer the angular momentum from the light to the atoms.
Pumping angular momentum into them.
Exactly. And by doing this, you can make the atoms preferentially line up in certain magnetic states, these M sublevels, either positive M or negative M.
So you're creating atomic orientation, like lining up tiny compass needles.
That's a good analogy. And because the electron's magnetic moment is coupled to the nucleus's spin.
You can also orient the nucleus itself. Nuclear orientation.
Wow. Right. The goal wasn't just orientation for its own sake. It was to create these very non-natural distributions.
Far from the normal thermal equilibrium. The Boltzmann distribution.
Way off Boltzmann. And then they could study how these highly oriented atoms relaxed back to normal, or how they responded to resonant radio frequency fields.
It sounds incredibly powerful, but I bet there were hurdles. You're dealing with delicate quantum states.
Oh, absolutely. Kastler himself admitted he didn't initially know much about the relaxation processes. How quickly would these oriented atoms get knocked out of alignment?
Collisions with the container walls or other gas molecules.
Exactly. Those were the big mysteries. But figuring them out led to some key breakthroughs.
Like the wall coatings.
Yeah, they found certain coatings like paraffin wax could dramatically slow down relaxation on the walls, made the atoms kind of slide off without losing their orientation as easily.
Clever.
And they realized that ground states, especially stable S states, were way less sensitive to collisions than the more reactive excited P states.
Okay, that helps.
And then the idea of using buffer gases. Inert gases that wouldn't interact magnetically.
But they get in the way of the oriented atoms colliding with each other or the walls?
Sort of, yeah. They slow down the atom movement, allowing work in simple sealed containers. Big simplification.
And discovering the relaxation times were similar, transverse and longitudinal.
Right. That was crucial. It meant the resonance lines they could measure were incredibly narrow, super precise.
Which opened the door to metrology, like atomic clocks.
Unexpectedly, yes. That precision was a bonus they hadn't fully anticipated.
It really speaks to the power of just diving deep into a problem.
Doesn't it? And after 1951, Kastler and Brossel really formalized this. They built a team in Paris.
Young researchers, students?
Yeah, a whole group systematically developing these optical methods, and they really started getting results.
A harvest of results, as the lecture puts it.
A rich harvest indeed. Detailed data on relaxation, super precise measurements of Landé factors, those atomic fingerprints.
Fine structure, hyperfine structure. All sorts of details about atomic states.
Both ground states and excited states. But what's really fascinating is that sometimes the results didn't match predictions.
The best kind of results. sometimes.
Often, yeah. These unexpected findings led to discovering all sorts of subtle, higher-order
Like
effects.
multiple quantum transitions.
Uh-huh. And Hertzian coherence affects these weird quantum synchronization effects within the atoms, resonance shifts caused by the light itself, even the radio waves changing fundamental atomic properties.
Wow. And other groups were finding things too.
Absolutely. Measuring nuclear quadrupole moments, studying exchange collisions where atoms swap states, hyperfine resonance shifts. It was a burgeoning field.
Okay, so things are getting even more interesting. Let's talk about deepening that understanding. There was this study by Blaumont.
Georges Blondet, yeah. On the Stark effect in mercury, that's the splitting of energy levels in an electric field.
And he found something odd with the 63p1 state.
Very odd.
Yeah.
He found that adding an electric field actually made the magnetic resonance curves narrower as the mercury vapor got denser.
Which seems backwards, right? More
Yeah.
density, more collisions. You'd expect broader lines, less coherence.
Exactly. It looked like it might contradict the uncertainty principle somehow.
But Brossel had an explanation.
A brilliant one. He proposed that these Hertzian coherences, the transverse magnetic alignment, weren't just dying out. They were being passed from atom to atom through the multiple scattering of the resonance photons themselves. The light bouncing between atoms was carrying this coherence information.
So the coherence gets trapped. Imprisonment of Hertzian coherence.
That's the term. It meant the coherence lasted longer overall, hence the narrower lines, like a quantum secret being whispered through the vapor.
That's quite an image. How do they prove it?
Rollet's work was key. He showed that the depolarization of the resonance light increased faster in a pure isotope compared to a natural mixture.
Why is that significant?
Because it showed the effect was due to photon scattering, which is stronger between identical atoms in a pure isotope and not just random collisions. It nailed Brossel's hypothesis.
And Jean-Pierre Barrat developed the theory behind this.
He did. The full quantum theory of coherent scattering, using density matrix formalism, it matched the experiments beautifully.
And the methods kept expanding. Electron impact excitation.
Yeah, Pibet-Perula and Descoudes showed you could use electron beams to excite atoms like helium, and then use these optical detection methods to study their fine and hyperfine structure.
And then another surprise, multiple quantum transitions.
Right. During the first optical pumping tests on sodium, they found atoms could absorb the energy of several radio frequency photons at once.
Making bigger jumps than expected.
Exactly, even if one photon didn't have enough energy. J.M. Winter then studied this systematically. Another layer peeled back.
Meanwhile, the practical techniques were also improving. Paraffin coatings, buffer gases.
Made optical pumping of alkali atoms much easier, much more reliable, and that directly led to discovering exchange collisions, atoms swapping spin states.
And understanding the walls better. Aimé Bouchiak-Yoshon.
She used those paraffin coatings to really pin down how relaxation happens at the container surface. Understanding that interface was crucial.
And Bernard Cagnac managed nuclear orientation in mercury.
Yes, in low-density vapor. A real achievement that allowed for incredibly precise measurements of nuclear magnetic moments.
And W. Franzen's transient method, watching the signal decay.
That let them directly study the relaxation due to wall collisions. It opened up whole questions in surface physics.
And J.C. Lehman's work on cadmium and zinc.
He oriented cadmium nuclei, measured their moments. His initial failure with zinc was actually quite informative.
How so?
It helps show that the nuclear orientation doesn't happen right when the light is absorbed. It happens slightly later during this intermediate stage where the nuclear and electron spins recouple. A subtle but important timing detail.
So the techniques kept getting more sophisticated. What about Demelt's crossbeam method?
Hans Demel, yeah. A very clever technique. It allowed optical detection of the transverse macroscopic magnetic moment of the whole vapor.
The overall sideways spin.
Sort of, yeah. A magnetic field makes this moment precess, like a tiny gyroscope.
And the second beam of light, the crossbeam, could detect this precession.
Exactly. The precession modulates the light absorption. So the light acts like a probe, reading out the spin dynamics.
And Claude Cohen-Tanucci refined this further with synchronous detection.
He did. Cohen-Tanucci, another future Nobel laureate working in this group, synchronous detection is super sensitive. It let them separate the in-phase and out-of-phase parts of that precessing signal.
Like seeing the different components of the wobble.
Precisely. Great for studying steady-state effects and also transient phenomena, what happens when you suddenly switch things on or off.
Like measuring relaxation times, T2.
Yes. If you switch off the pumping beam and the radio frequency field, you can watch the free precession decay. That decay rate directly gives you T2, the transverse relaxation time.
And Cohen Tanuji also used these techniques to study tiny energy shifts caused by the light itself.
Right. Shifts predicted by quantum theory, he showed there were two kinds,
Real transition
where the atom absorbs light and actually jumps between states,
and virtual transitions.
where the light frequency is close to an absorption frequency, but not quite right. The light isn't absorbed, but it still interacts fleetingly.
How does that show up?
As a change in the light speed through the vapor abnormal dispersion, and, incredibly, a tiny shift in the atom's ground state energy level. The light itself slightly alters the atom's baseline energy.
Wow. Even the Landau factor could change.
Even the Landau factor, depending on the radio frequency field strength. These are really subtle quantum effects made visible. Russian physicists even managed to amplify these shifts using ruby lasers later on.
So these methods weren't just for isolated atoms and gases.
Not at all. Jean Margerie showed they could be applied in solids, too. To paramagnetic ions, to F-centers, those electron traps in crystals.
Why is that so important, extending it to solids?
Because it gives you incredibly precise information about energy level structures, even when they're too close together to be resolved by normal spectroscopy. You can see details hidden from other methods.
It really opened up a new level of detail across different states of matter.
It absolutely did.
So what a journey we've taken. From just wondering how light and atoms interact,
Through failed experiments, brilliant insights, careful technique development.
optical pumping, double resonance, Hertzian coherence, it's incredible. Seeing how understanding angular momentum let them measure and manipulate atoms with such precision, even trapping coherence.
I think the real aha moment here, for me at least, is realizing how much information is encoded in light. Just by carefully watching how light changes its polarization, its intensity, how it interacts with these fields.
They could deduce unbelievably precise details about the hidden inner workings of atoms.
Exactly. Phenomena you couldn't imagine seeing directly, revealed just by observing light. It's like learning a language the universe speaks.
So bringing it back to you, our listener, what's the takeaway? Well, think about how these seemingly abstract ideas, like optically pumping atoms to orient their nuclei,
Are actually the fundamental building blocks for technologies that are still emerging.
right? If we have this level of control, this ability to measure individual atoms and their quantum states, what other mysteries are out there? What comes next?
Well, revolutionary applications might pop up. Quantum computing, ultra-precise sensors, maybe new medical imaging techniques we haven't even conceived of yet. The foundation laid by Kastler and his colleagues is still being built upon today. The discovery really does continue.